Hello, today in our lesson, we're going to look at how the law of universal gravitation can be applied to the interaction between the Earth and a body. Why is there a lot of emphasis on this? Simply because we're on this planet and of course we're interested to know how the Earth attracts us to it and what parameters can be used to describe that interaction. Let's draw a picture of this situation and try to describe it in terms of known laws. Also, for example, we have a planet called Earth, which you and I know in terms of certain parameters. So we know the mass of the Earth, we know its radius, we know the basic values that we need for this description. For this description, we have them. In any case, we can find them in certain reference books. And then, of course, the question arises how the Earth attracts certain bodies to itself. That is, by what force it happens and how we can describe this attraction. Let's take, for example, a certain satellite that revolves around the Earth in a circular orbit and is in that orbit because of course, the Earth's gravity. In this case, there's a certain force acting on this satellite, which we'll denote by this. This is the only force that acts on a given satellite, and therefore we can confidently assert that the satellite is in continuous free fall during its motion. But the only thing is, having the required velocity, it does not eventually fall to the Earth. Now the question arises how to calculate the force of interaction between the satellite and the Earth. In this case, you and I must know a certain distance to this satellite. Let it just be the letter r. Yeah? And then to calculate the force of attraction of the satellite to the Earth, we apply this formula. Let's denote the mass m small, that's the mass of this satellite. And divide by the distance. Now what distance we are going to talk about here? In this case, when we consider spherical objects, when these objects interact with each other or when these objects interact with other bodies, we can think of them as material points. But the only point is that we collect the mass of that material point at the center of that object. So when we talk about the distance between, for example, a satellite and the Earth, we take the distance between the satellite, which of course is small compared to the Earth, and the center of the Earth. And that is, this distance will include, as we see in the figure, the radius of the Earth and the distance from the Earth's surface to the satellite itself, that is, the height of its orbit. But in general case, we have this formula, and now the question arises whether we will always have to calculate the gravitational force using these not quite convenient for calculations, like the gravitational constant, the mass of the Earth, the radius of the Earth. Isn't it possible to simplify this expression so that you can quickly calculate the gravitational pull of the Earth and any object in particular? Indeed we can. Let's try to do that, given that, as you and I can see, there are certain constants that you and I can, based on some constant values for the Earth. Or for example, if we're on the surface of the Earth, we can calculate how much force the Earth exerts on a single mass, a 1 kilogram body, and then we can simply multiply this coefficient by the mass of a particular object and get the final force. It's a much simpler calculation than using the formula all the time in this format. If you and I now want to calculate the gravitational force between a body and the Earth, and the body is on the surface of the Earth, well, we're going to use the formula. G times the mass of the Earth by the mass of the object and divide by the radius of the Earth squared. Here you and I see three constant quantities that specifically for the Earth remain unchanged. This is, of course, the gravitational constant, a universal constant for all objects. Then the mass of the Earth and the radius of the Earth squared. That is, we can separate these three constants into one constant, which can be labeled with a certain letter. In this case, this constant is usually denoted by the letter g small. And so, according to this formula, we end up with the following pattern. For the Earth, we get the following pattern. Now all that is left is to put numerical values and calculate the acceleration of free fall, which is what this parameter is called, on the surface of the Earth. Let's put numerical values for the gravitational constant. It's 6.67 times 10 to the minus 11th power. Not that, but multiply by a meter squared, divide by a kilogram squared. kilograms squared. Then the mass of the Earth, if we take it from the reference books, it's about 6 times 10 to the 24th power of a kilogram. And the radius of the Earth is roughly equal to 6.37 by 10 to the 6th power of a meter. So of course we take the radius of the Earth squared here. Once we've done this calculation, we have an approximate value for our gravitational constant, which is directly the acceleration of free fall. 9.81. Well, in dimensionality it will be Newton divided by kilogram. But as we know, we can also write the Newton as a kilogram, multiplied by a meter and divided by a second squared. If we also divide by a kilogram, then we reduce the kilogram and we end up with the acceleration dimension. So for the Earth on its surface, we've got this value. And now the gravitational force of a particular object. To the Earth we can already write with the help of a simplified formula, replacing all these constant values for the Earth by its constant. As a result, we get a formula that allows us to calculate the force of gravity of a particular object on a given planet. As you and I realize, we can use this formula for any planet or satellite of spherical shape. All we need to do is to know the mass and radius of these objects. What do we do when we are moving away from the surface of a given object? In this case, we must write that the given freefall acceleration already takes the form of, taking into account the added distance, which we denote by the letter h, and the formula will then look a little different. Taking into account the update, we see that only the distance increases. The mass of the planet remains unchanged. The radius of the planet we also take as a fixed value. You can change only in this case the height h. And of course it's very important to note that this formula will only work if you're moving from the surface of the planet to somewhere in space. If we try to go inside the planet, it will work a little bit differently in this situation, and we will talk about it for our future classes. And the last point is that, as far as our nearest neighbors are concerned, it is interesting to know what gravitational parameters exist on the Moon. To do this, of course, you need to know its mass and radius. And you can also look it up in special reference books. But in fact, we can tell you right off the bat that the same Moon, which also has a certain size and mass, let's label it this way, will be calculated based on the law of gravitation using the same formula. Accordingly, after setting, you and I will get a value for the acceleration of free fall of about 1.6 of a meter per second squared. So this free fall acceleration is about 6 times less than on Earth, so the Moon's gravity is about 6 times less than on Earth. And so if you try to do a jump on Earth, pushing off the Earth with a certain amount of force, you'll go up to a certain height. But if you do the same thing on the Moon, you'll be 6 times as high relative to the surface of the Moon. All of this is due, of course, to the reduced gravity of this celestial object. So this is how the law of universal gravitation works in terms of calculating one very important parameter, which we have derived today. It is the acceleration of free fall, and further, of course, in the tasks we will use a ready-made form for calculating such values. This is the end of our lesson. Goodbye.